Well, hello students in Honors Math 1, this is Mr. Roberts, and I'm going to go through the entire test for Chapter 2. This is the Chapter 2 test walkthrough. First question, it says given the equation of the line, or rather, give the equation of the line that matches the given information. So there's 4 scenarios here, and in each case we're asked to write the equation of that particular line. Let's look at the first one. The first one says this line has a y-intercept of 2/3. So that y-intercept is the place on the y-axis where the line will cross. And I'm told that the y-intercept for this one is at 2/3. And it has a slope pattern of 5, which means from the 2/3 it would go up to 5 2/3 and over 1. 5 2/3 over 1. So this line is y is equal to 5x plus the y-intercept of 2/3. So y equals 5x plus 2/3. Next question. It says this line has a slope of 3/4. So we do know the slope. The slope is 3/4. I'll go ahead and label this m because it's one of our 2 parameters when we're writing down the equation of a line in slope-intercept form. The other thing we're told is that it has an x-intercept of y, right? So I'm reading that closely. It's an x-intercept of y. It turns out an x-intercept means somewhere on the x-axis this line is crossing, and it happens to do so way over here when x is 12, and the moment that x is 12, y would equal 0. So I didn't write that very well, but what I'm saying is I've got this point. 12 is x, and 0 is y. So because of that, I really have here a point. I know a point, and I know the slope, m, but I don't know the y-intercept. I do know that any line, except for vertical lines, can be written in the form y equals mx plus b. And because of that, because that's true, right? So, as a result, I can say that y minus m times x will always equal my y-intercept. So, I've got my slope, but I don't have the y-intercept, so I need to find this, b. And to find it, it's pretty straightforward. It says, oh, you're just going to need a y value. I've got it at 0. You're going to need to know an x value. I've got that. It's 12. And you're going to need the slope. And I have that. It's 3/4. So I'll write all those things down. First, I start with y. Y is the number 0 minus my slope, which is the number 3/4. And then I'm going to multiply that by x, which in this case is 12. And this will equal b, my y-intercept. Well, on my calculator, I can do this. 12 divided by 4 is 3. 3 times 3 is 9. This is -9. So 9 is my value of b. I've got my y-intercept now. It's happening at -9. So the equation of this line for b is y, grab the pen, y is equal to 3/4 times x minus 9. So now we've got both A and B. I know the test says write the answers in the space provided. I'm not going to go over there for the video, but please keep doing that. Thank you for recording your answers like that. Next question, C, says this line goes through the point. So we're given 2 points. One of the things we know that is if we have 2 points, right, we can look at and identify a slope triangle. Right, so for any 2 points, we can look at a slope triangle. On that, we can identify our rise, which are change in y, and we can identify our run, which is the change in x. We're going to just do this without drawing the triangle. We're just going to look at, hey, here's a y value, here's a y value. So my change in y's are going to be the green values, and then here's an x value, -6. Here's an x value, 34. My change in x's are going to be those purple values. So if I go ahead and do this, whoops, I've got my change in my y values divided by the change in my x values. And for y, I'm going to go 13 minus 3, 13 minus 3. And for the change in my x values, I'm going to follow that same pattern. I started with the first point there. So I'm going to start again, and I'll grab 34 minus, and then a -6. So in my numerator, I have 13 minus 3, which is the number 10. And in my denominator, I have 34 minus -6, which is 34 plus 6, which is 40. And if I divide both of those by 10, there's a common factor of 10. I get that my slope is the pattern up 1 over 4. So we now have our y-intercept. It is occurring at, it is 1/4, up 1 over 4, up 1 over 4. Same thing I just did for part B, I'm going to do again. I'm going to say, hey, any line can be written in the form y equals mx plus b as long as it's not a vertical line. So this is a line, and I can see that it's not vertical because my x values are different, so I'm not worried about that. So I'm just going to say, look, I'm going to take my y value and I'm going to subtract mx. I'm just taking this equation, subtracting mx from both sides. Y minus mx is going to give me my y-intercept b. Well, okay, let's go ahead and use this for y. Oops, that would be wrong. That's x. Let's use this for y, and we'll use the 34 for x. And we know our slope is 1/4, so we can calculate our y-intercept b. So I'm going to write y, which is 13, minus 1/4 times x, which is 34. And this will give me my value of b. So I'm grabbing a calculator here. I'm going to go 1/4, 0.25 times 34. That's half and half of 34. That gives me this number. Oh, no, I did that wrong. 0.25 times 34. That gives me 8.5. And then I'm going to go ahead and take 13, and I'm going to subtract 8.5. 13 minus 8.5 gives me 4.5. And if I want to, I can look at that as a decimal. It is 9/2. 9/2 is my y-intercept b, which is also 4.5. So I have everything I need to know. I know both parameters, and it's not a vertical line, so I can write the equation of the line. It is y is equal to 1/4 times x plus 9/2. Perfect. We now have the equation of the line for C, y equals 1/4 plus 9/2. And then let's go on to the last one. The last one, part D, we have lots of values because you're having an entire table here. So for this table, it really doesn't matter which values I use. I still need to look at the change in y, and I need to look at the change in x's. So I'm going to go ahead and say, let's look at the change in y, and we'll look at these values for y. We'll look at 10 and 4 for my y values. And for the x values that goes with them, we're going to look at the 3 and the 12. So we're looking at 310 and 12:4. And again, we need to take our change in y's. That's going to be in our numerator. And we're going to divide that by our change in x's. That's going to go down in the denominator. And when I do this, right, we've got my change in y over change in x. I'm going to go ahead and just take the top point, 10, and I'm going to subtract 4 for the numerator, 10 minus 4. And for the denominator, I'm going to take 3 and subtract 12. So I just follow that same pattern. I took the top, subtracted the bottom. 10 minus 4 over 3 minus 12. 10 minus 4 is 6. 3 minus 12, I believe, is negative 9. Those both are divisible by 3. There's a common factor of 3. 6 divided by 3 is 2. And 9 divided by 3 is 3. Only one of those two differences was a negative number, so this is a negative slope. So I'll just say the slope is negative 2/3. Right? Down 2 over 3, down 2 over 3 is the slope pattern. Okay, so now we know our slope, and I have lots of points that I could pick, and every single one of these is going to give me the exact same y-intercept. Doesn't matter which one I pick. I'm going to go ahead and select this point. I'm going to use y is 16. I'm going to use x is negative 6. And I'm going to just remind myself this is not a vertical line because my x's are all different. For any line, it is true that y, we can write that line in the form y equals mx plus b. I'm trying to figure out what my y-intercept is, so I'm just going to subtract mx from both sides. So that means y minus mx will give me the value of b, my y-intercept. So the y value I'm using is 16, and I'm going to subtract from that the number negative 2/3. So I've got 16 minus a negative 2/3, and my x value is going to be negative 6. And this is going to equal b. So on my calculator, I'm going to first of all do negative 2/3 Beautiful. And I'm going to multiply that times negative 6. And when I do that, I get positive 4, right? That's negative 2/3 times negative 6. 6 divided by 3 is 2. 2 times 2 is 4, and it's a negative 2 times a negative 2. So this is a positive 4. So now I have 16 minus 4 as my y-intercept, and 16 minus 4 is 12. So my y-intercept B is 12. And now I know both parameters, right? So I can write the equation of this line. This line is y is equal to negative 2/3 times x plus 12. So that is it for question number 1. We have all 4 equations. Let's move on to question 2. It says, given the input, identify the output of each function. So we are given the input value and asked to identify what the output was. So first of all, for this for part A, f of x is defined as the quantity of 2 binomials, right? It's 3x plus 1 times the binomial x plus 2. So something times something. So I'm just going to go ahead and do some substitution here. So I've got 3 and then open paren 3. And what I just did right there is I took my value of x and I placed it right there. I'm going to do that again right here. So that was the first x that I substituted in. I'm going to add to that 1, close parentheses, open paren, and then I've got my x value. I'm going to put a 3 inside of another set of parentheses. Right, that's the second x that I'm substituting in, and then plus 2, and I'll close the parentheses. So all I've done is I've replaced x with the value of 3 everywhere I saw it. Let's look at the first set of parentheses. 3 times 3 is 9, and 9 plus 1 is 10. So this is the value 10. 3 times 3 is 9. I'd have to do that multiplication first, and I added 1, I get 10. And on the other side, I have 3 plus 2, which is 5. And when I multiply these two values, I get the number 50. So when 3 goes into this function produces an output of 50. So 50 is the output for that function when x is 3. Let's go take a look at B. B says, please place negative 4 into this function. So negative 4 is going to go in 2 places. It's going to go here and here. And I remind myself I'm placing a negative 4 in there. So in the numerator, I'm going to have a negative 4, and I'm going to add to that 40. And then in my denominator, I'm going to have a negative 4. One thing I did see is quite a few of us looked at this and claimed that negative 4 over negative 4 was the value of 1. It would be if this operation was multiplication, but it's not, it's addition. So our numerator has 2 different terms. So we can't just look at this and claim it's 40. We have to add here. So negative 4 plus 40 is positive 36 in our numerator. And in my denominator, I have negative 4. And if I take positive 36 and I divide that by negative 4, I get the value of negative 9. So when negative 4 goes into this function, negative 9 comes out as the output. Right, let's move on to question 2 on page 2. I'm sorry, question 3 on page 2. This question says, hey, look, this time I'm telling you that the output is negative 14. The question is, what is the input that would produce that output? So understand what we're trying to do. We're trying to find out what value of x, right? What value of x would make this thing become the number negative 14. So what I'm going to do is I'm going to take this expression that represents f of x, which is 4 minus 3 times the quantity of 5x minus 1, and I'm going to set that equal to negative 14. And I'm just going to solve this equation, and it's going to tell me what value of x makes this expression equal negative 14. So first of all, we're going to begin with the simplest form of the distributive property. This is going to become a 4 minus 15x plus 3 equals negative 14. I can combine the positive 4 and the positive 3, and I get 7 minus 15x equals negative 14. Next, I guess I'm going to divide both sides, or no, I'm going to subtract 7 from both sides. If I subtract 7 from the left-hand side, this 7 is going to not exist here anymore because 7 minus 7 is going to make a 0. So this will leave with negative 15x. And when I take away 7 from the other side, and you can confirm this with your favorite calculating device, you get negative 21. So it looks like in order to figure out what x is, I just have to take negative 21 and divide that by negative 15. So this is my first look at what x is, and I can simplify this in many ways. One of them is I could just go ahead and fire up our classroom calculator and look at it there. Or I can remind myself, hey, both of those are divisible by 3, and they're both negative. Both the numerator is negative and the denominator is negative, so I know the result is going to be positive. 21 divided by 3 is 7, and 15 divided by 3 is 5. So it looks like that 7/5 will produce a value of negative 14. One thing you can do is, now that you have a pretty good idea that 7/5 is the value that will do this, you can put this in here and check it. 7/5 times 5 would give me just 7. 7 minus 1 would give me 6. And then this would become what? 4 minus 3 times 6. 4 minus 3 times 6 is 18. Yeah, 4 minus 18 is negative 14. So when x is 7/5, this function does indeed produce an output of negative 14. So the answer is 7/5. And then B, the second part of question 3, it says, hey, what value of x produces an output of 5? So this is the definition of the function, 8x plus 1, and I want to know what value of x will produce an output of 5. So I just make that equal to 5. Subtract 1 from each side, 8x is 4. Divide both sides by 8, and I get x is 4/8, which is 1/2. So 1/2, if I plug 1/2 into this function, it's going to give me an output of 5. So the input is x is equal to 1/2. All right, moving on to question 4. There were 4 parts to 4, A, B, C, and D. Let's look at the first one. On this first one, the only numerical coefficient I see is 3. That 3 is not going to be multiplied by anything else. So I'll remember there's going to be a 3 in my answer. That's going to be the leading term. And I can also see that I'm multiplying bases of x. In fact, I've got 2 factors of x, I've got 5 factors of x, and I've got 5 more factors of x. And y, in terms of y, there are 6 factors of y here, and then there's a y to the negative 4th power here. So my answer is going to look like this. I'm going to have a value of 3, and then I'm going to multiply by some x's. How many x's? Well, x times x times x times x times x times x times x, that's 7, times x times x times x times x times x, that's 12. So it's going to be 3x to the 12th. You don't have to count like that. You can just add. 2 plus 5 is 7, plus 5 is 12. And then in terms of y, because 4 of those factors are negative, right, I could put them in the denominator and simplify it, but I could just also add negative 4 plus 6 is 2. So it's going to be 3x to the 12th, y to the 2nd power. That's exactly what this expression is equivalent to. You pick any favorite values of x and y you want, and both of them, both the original one and this new version, will always produce the same outputs. Let us move on to part B. Part B, I'm going to, because it is a fraction, I'm going to go ahead and identify and just write this as some ones that I can get rid of. So in my numerator, I do have 6, which is 2 times 3. And I see that I've got x to the 9th in the denominator. So I'm going to break up this x to the 12th power as x to the 9th times x to the 3rd. And that's all going to be over 15 is 5 times 3, and then times an x to the 9th. So you can see that there is some clear common factors here, and because they are factors, it's not addition, they do form the number 1. So I've got 3 times x to the 9th, 3 times x to the 9th in both the numerator and denominator. So what I'm left with is in the numerator, there's a 2x cubed, and in the denominator, there's just the value 5. So this expression, 16x to the 12th divided by 15x to the 9th, is the same. This expression is the same as this expression. You give it any favorite value of x, it's going to produce the same outputs. Moving on to A, B, C. Okay, so I see that I have the second 3x. There's a 3x squared, and then there's a 3x squared that's being raised to the second power. So there's a 3x squared. There's a 3x squared. But then there's this other thing. There's this 3x squared that's getting squared. Let me underline that in green. There's a 3x squared that's getting squared, a 3x squared that's getting squared. Well, the 3x squared I'm just going to write as 3x to the second power. But the 3x squared that's getting squared, right, that means that there are two identical 3x squareds times another 3x squared. If I multiply that, 3 times 3 is 9, and x squared times x squared is x to the fourth power. So this is 9x to the fourth power. 3 times 9 is 27. X times x times x is x to the sixth power. So the answer for C is these two expressions. 3x squared times the quantity of 3x squared is the same as 26 times x to the sixth power. And then our last problem. So we've been dancing around this, looking at these for a while, and we're going to continue to look at some negative exponents. One way we can tackle this is we can look at some of the laws of exponents, and these are written on the wall in the classroom. If you have x to the m power, and you're dividing that by x to the nth power, that is the same as x to the m minus n. It's the same as that. So if I look at this, playing the part of m is the number 5. M is the number 5. And playing the part of n is the number negative 5. Is negative 5, right? So so I could just say, hey, this is going to be the same as x to the 5 minus a negative 5. 5 minus negative 5 is 10. So this is x to the 10th power. And let's not forget there was this factor of 2 that was in the numerator to start with. Turns out I don't have a denominator anymore, so I'll just place this 2 right there. So 2 times x to the 10th is one way to get this. Another way that I've talked about a few times, and I'll talk about this more, is introducing a value of 1 that'll destroy this negative exponent. So if I look at this negative exponent in the denominator, if I multiply that by x to the positive 5th, that will make the denominator x to the 0 power, right? Because negative 5 plus 5 is 0. And anything to the 0 power just simply equals 1. So in the denominator, we're going to get a 1. But remember, I can't just multiply by any random fraction like this, but I can multiply by exactly the number 1. So what I'm doing here is I'm introducing a 1 to multiply by. And when I do that in my denominator, I get x to the negative 5th times x to the 5th, which is x to the 0, which is equal to 1. So I get just a 1 in the denominator. And my numerator is 2 times x to the 5th times x to the 5th, which is 2x to the 5th. So it's kind of like it's two ways of seeing the same thing, right? All right, let's move on to question, there was 4. Let's move on to question 5. 5 asks us to solve each equation below for the given variable. So we will start with A. Any way you can just slow down, write as clearly as possible, kind of exaggerate good handwriting. It really helps reduce errors. The first thing I'm going to do is I'm going to rewrite a chunk of this equation. Rewriting is a pretty good strategy for solving equations. And I'm going to replace that with something that's equivalent to it. So I'm going to replace that with a 4x minus 8. So this is going to become, I've got my 2x plus 1 plus 4x, and then 4 times negative 2 is minus 8. And on the other side, we know that that is the number 11. When I combine 2x and 4x, I get 6 times x plus 1 minus 8 equals 11. And I know a lot of you are saying, Mr. Roberts, why didn't you deal with the 1 and the negative 8 at the same time? It's because I like to very clearly look at step by step and say, what's the one thing I did? So for example, in the first step, the one thing I did was I rewrote a portion of that equation using the simplest form of the distributive property. And the next part, I rewrote it by combining 2x and 5x. In this next part, I'm going to combine it by combining positive 1 and negative 8. So I get 6 times x minus 7 is 11. Oops. Yeah, and then in the next part, I'm going to add in 7 to both sides. So I get that 6 times x is 18. That's adding 7. And I'm going to divide by 6. So I get that x is 18 over 6. And 18 over 6 is the number 3. So x is 3. So there we go. X is 3. If I take that value 3 and I plug it in to the original equation, it will indeed produce 11, the value of 11 on both the left-hand side and the right-hand side. And in a previous video, I definitely talked about how you can do this with the classroom calculators. If you're interested in perfecting that technique, because it's a really quick way to check equations, talk to me and I'll show you. I'll show you that. All right, and then B, same deal. Solve this. I'm going to rewrite two portions of this equation. I'm going to rewrite this portion. I'm going to rewrite this portion. And so now I'm like, I think I'm going to do two steps in one. Yeah, but they're both rewriting, and they're not gonna overlap, so they'll be on two different sides of the equation. I should be able to keep it track. I think even I can keep track of that. So I'm gonna have 4x minus 3x minus 6 plus 11. That is my left-hand side, and I distributed the negative 3 to both the x and the positive 2. And on the other side, that's going to equal 6 times x minus 30. I will combine like terms on the left-hand side. 4x and 3x is just going to be a single x, minus 6 plus 11. And on the other side, it is 6x minus 30. Next, if I combine negative 6 and positive 11, that's going to give me positive 5. So this is going to become x plus 5 equals 6x minus 30. I'm going to subtract an x value from each side, so 5 is 5x minus 30. I'm going to add 30 to each side, so 35 is 5x, and I'm going to divide both sides by 5. 35 divided by 5 is x, and it turns out that 35 divided by 5 is the number 7. So x is 7 is my solution for this second equation. That was question 6. We are on to question 7. No, that was question 5. My bad. Excuse me, that was question 5. Let's go on to question 6. 6 says, evaluate the given expressions, and I'm told what A, B, and C are. So this first equation, so A, B, and C are negative 4, 2, and 12, right? Negative 4 is A, B is 2, and C is 12. So let's see. Here is A. A is negative 4, and I'm going to multiply that by B squared. Okay. Then I'm going to subtract 16, and then I'm going to subtract C, which is 12, right? I'm going to subtract 12. C was positive, but this was subtraction, so I'm subtracting 12. In my denominator, I'm going to multiply 5 times B, and B was 2. So if I look at my numerator, there's this exponentiation of 2 squared. I'm going to do that first. So 2 squared is 4, and then I'm going to multiply that by negative 4. So 4 times negative 4 does give me negative 16, and then I had another negative 16, and then I had a minus 12. And in my denominator, I've just got the number 10. Negative 16 minus another 16 is 30. What is that? It's negative 32. And if I subtract another 12, I think it's negative 44. So I believe my numerator is negative 44, and my denominator is 10. I do know both of those can be divided by 2. I know that I know 10 can, so 10 divided by 2 is 5, and negative 44 divided by 2 is negative 22. So it looks like it's negative 22 fifths, and there is a decimal equivalent to that that's pretty reasonable, so you could probably just write down what is it, like negative 4.4, and that would work as well. All right, and part B, this is a recurring item, right? On B, I'm asked to square A, and A is the number negative 4. So I see many of us writing this down, like we'll write negative 4 squared just like that. Unfortunately, that's not what this is asking us to do. And if I entered that in my calculator, it would say negative 16. It says that I need to square what A is. So our book has said this. It's really advisable when you're evaluating expressions to use extra parentheses. So I'm just going to say, hey, here is negative 4, right? All of A is placed exactly in those parentheses, and I'm going to square that. So writing it down this way indicates very clearly that this is negative 4 times negative 4, which is positive 16. And then I've got plus 5 times 2, and then minus 12. Negative 4 squared is 16, plus 10 minus 12. Okay, so 16 plus 10 is 26 minus 12. And if I have 26 and I take away 12, 6 minus 2 is 4, and 2 minus 1, I get 14. So 26 minus 12 is the number 14. All right, I think we are on to our, this is the last page. We're on to our second last question, number 7. Number 7 says, Mr. Roberts and Mr. Woolard are racing their tricycles on the Shasta track because Mr. Roberts is older and slower. I'll own it. He was given a 4 meters head start. He was given a head start of 4 meters, and he travels at a speed of 3 meters every 2 seconds. So let's try and graph that first. So we're asked to accurately plot the race in a graph, and we're actually also asked to write equations that represent the progress of the racers. So I'm given a 4 meters head start. That means on the x-axis, when time is 0, meaning they haven't said on your mark, get set, go yet. When time is 0, I'm sitting here at 4 meters. And then for me, it says I get to travel 3 meters. That's 1, 2, 3 meters every 1, 2 seconds, right? 1, 2, 3 meters every 1, 2 seconds. So this looks like the progress for me as a racer, starting at 4 and going up 3 over 2, up 3 over 2. So this line right here, we will label as Mr. Roberts. The other racer, Mr. Woolard, says at the start of the race, Mr. Woolard does not pedal for the first 3 seconds. And I know why. He's confident. I'm not a threat. He's going to win this race. So what does he do? He just sits there and he does not pedal for the first 3 seconds. So you can imagine they say on your mark, get set, go, right? And I'm going along here. There's my 1 second, 2 second, 3 seconds. But what's Mr. Woolard doing? He's just sitting here for 1 second, for 2 seconds, for 3 seconds. Now, at this point, right, he's waited a full 3 seconds, and then it says then he traveled at a constant speed of 5 meters per second. So from here, it's up 1, 2, 3, 4, 5 seconds per 5 meters per every second. So he goes here next. 1, 2, 3, 4, 5 over 1. So I'll grab this line tool and I'll show the progress of Mr. Woolard in blue. So writing the equation for Mr. Roberts is pretty straightforward because I can see both my y-intercept and I also see the slope triangle, right? I can see a rise of 3 and a run of 2, and the y-intercept is at 4. So this equation is y is equal to up 3 over 2 times x plus the head start of 4 meters. Mr. Woolard's equation is a little bit more difficult because I don't see his y-intercept. I mean, I could imagine that if I extended downward, somewhere down here, it's way down here somewhere. So I know it exists, but it's not visible to me. However, I do know that I have multiple points that I know about Mr. Woolard. So for example, I know whoops, wrong tool, I need the line tool. I know that at 3 seconds, he's 0 meters from the starting line. And I know at 4 seconds, he's now 5 meters from the starting line. And I also know that at way down here at 5 seconds, he's now 10 meters from the starting line. So I have a bunch of points that lie on Mr. Woolard's line. So if you think about it, I know two things. I know a bunch of points, and I also know his speed of 5 meters per second, right? So I know his slope. His slope m is 5 meters per 1 second, or just 5. So how do I find his y-intercept? Well, it's a lot like question, was it question 1b? On question 1b, we were given the x-intercept, and that's what we're given here, right? We're given his x-intercept is at 3. What I would have to use is one of the points, and it doesn't matter which one, right? I could use this point, I could use this point, or I could use this point. But I just need to pick one of them and use the fact that, hey, because this is a non-vertical line, I can write its equation in the form y equals mx plus b, because it's not a vertical line. Right? That's the only exception. That's the only time you can't use this form of a linear equation. You could definitely pick other forms you like, but this one will always work as long as the line is not vertical. And I can see it's not vertical because all of my x's are different. So because I can use this line, it's true that y minus mx, right, is always going to be my y. It's always going to be my b. It's always going to be my y-intercept. So this right here is a very convenient and quick way of figuring out what the y-intercept is. That just says use the x value and y value from a point and use your slope, and you can calculate what the y-intercept is. And it doesn't matter which one I pick, they'll all give me the same thing. So for example, I'll use the one up at the top here. On this top one, I'm going to use x is 5 and y is 10. So I can say, hey, 10 minus, my slope was 5, so 10 minus 5 times 5. Right, so because my x value is 5, so that's y 10 minus slope 5 times x 5. Well, 10 minus 25 equals negative 15, right? So I've got my b value is negative 15. And because this isn't real paper, I can erase this, and I can do it with a different point. Right? If I did it with the middle point there, my y value is 5, so I'd have what? 5 minus, that's y. Y is 5 minus my slope 5 times my x-intercept of 4. What do I have now? I've got 5 minus 20. 5 minus 20 is still negative 15, right? And even if I take, let's just erase just the x and just the y, even if I take this other point and use the 0 for y and the x is 3, what do I get? I get 0 minus 5 times 3, and 0 minus 15 is negative 15. So in every single time, this is saying way down there, right? Way down somewhere, at negative 15 is the equivalent of Mr. Woolard's head. It's almost like by him waiting 3 seconds, it was like a 15, it would be the same as him starting 15 meters behind the starting line, right? Waiting 3 seconds for him, because remember, every single second for him is 5 meters. Oh, that's another way to think about that. That's cool. Every second is 5 meters for him. So each second that he waits is like he's having a 5-minute pushback from the starting line. So he goes back 5, 10, 15 meters from the starting line. So his equation, to summarize, is y is equal to 5, which was his slope, times x, minus 15. That's his y-intercept. Question 8 says, in another race, Miss Fifield travels at a constant speed of 12 feet per second. We're asked to convert this into miles per hour by using giant ones. You must clearly show your work to earn credit. So I did have on the board giant ones regarding miles and feet. It's not, I think a lot of us know that 5,280 feet is exactly 1 mile, but it's not something that we're required to know. So I did have that on the board as a reference. But we are starting with the fact that we're going 12 feet per each second. Now, 12 feet per second is, I can also write this as 12 feet per 1 second if I want. So I clearly see what's in the top, what's in the bottom. So I'm going 12 feet per 1 second, or 12 feet per second. I'm asked to convert this into miles per hour, and I'm going to start by dealing with time. So the first thing I see is I've got seconds in the denominator that I don't want in the denominator, so I'm going to put seconds in the numerator. And I know something about seconds and minutes, so I can do this conversion. I know that exactly 60 seconds is the amount of time that's equal to 1 minute. So again, why can I just randomly multiply by 60 seconds is 60 seconds over 1 minute? Because that's the number 1, right? 60 seconds over 1 minute is the same amount of time, so this is a 1. And then I'm going to multiply that by, I want minutes to go away, so I'm going to put minutes in my numerator, and I'm going to put hours in my denominator. And I know that 60 minutes is the same amount of time as 1 hour. Why can I just randomly multiply by 60 over 1? It's because it's not 60 over 1. It's 60 minutes over 1 hour. That's, again, the same exact amount of time, so that's the number 1. So if I look at where I'm at so far, it looks like my seconds have canceled, and it also looks like my minutes are gone. And what I'm left with is, in terms of time units, is I'm left with just hours. So right now, just looking at the units, I don't know what the number is yet. I know that I have feet per hour. Feet per hour. The last thing I want to do is I want to get rid of feet, and I can see my feet are in the numerator. Mr. Roberts, get your feet off the numerator. No, the feet, the units are in the numerator, so I'm gonna put feet in the denominator, and I'm gonna put 1 mile in my numerator. So I'm gonna cancel the feet that are sitting in my, I'm gonna cancel the feet that are sitting in the numerator with these feet that I'm placing in the denominator. Now, I can't just randomly multiply by a mile over a feet. I have to make this equal to 1. To make this equal to 1, I use the fact that 1 mile is the same as 5,280 feet. So 1 mile is the same distance as 5,280 feet. So I'm multiplying by 1, which means I'm not changing this unit. So what am I left with in terms of units? What I'm left with is, in the numerator, I have miles, check. And in my denominator, the only units that are left are hours, check. So the arithmetic I see here, like I've just done the math, right? That's the math. The arithmetic I'm left with will have the units of mile per hour. So let's do the arithmetic. The arithmetic looks like I have to multiply 12 times 60 times 60. And those are the only numbers that aren't 1 in the numerators. And in my denominator, I've got a 1, 1, 1. But the only non-1 that I have to concern myself with is 5,280 feet. So I'm going to grab a calculator, and maybe you want to grab your own calculator, but I'm going to use the fraction template. In my numerator, I'm going to enter 12 times 60 times 60, and in my denominator, I'm going to enter 5280. When I do that, my calculator says that reduces to 90 over 11. So 90 feet every 90, no, the feet are gone, Mr. Roberts. It's 90 miles every 90 miles. Hello, miles every 11 hours. And if I want to turn that into a unit rate, I just take 90 divided by 11, and it gives me what? 8.18 miles. No, not mels. M-I-L-E-S. Why? The pen does not like this corner of the screen. M-I-L-E-S per hour. Right, that is it. We're at about 44 minutes. If you'd like to discuss any of these with me, you know where to find me on campus. I'd love to talk to you about any thoughts you have, or maybe other insights or tricks you have to make your workflow easy. I hope you found this helpful, and I look forward to see you in the classroom.